A new study finds the supervolcano below Yellowstone National Park is much larger than previously thought.
Scientists have discovered that over 86,000 earthquakes took place under Yellowstone National Park in the United States.
Beneath the sweeping landscapes of Yellowstone National Park lies one of Earth's most enigmatic and formidable geological structures, a supervolcano whose very name sparks a quiet undercurrent of awe and unease. For decades, the Yellowstone caldera has been the focus of intense scientific scrutiny, with researchers constantly refining their understanding of the forces that slumber beneath its majestic beauty. Recently, however, a team of scientists unveiled new findings that have redefined the scope and scale of the magma system beneath Yellowstone, sending ripples through the global scientific community. These revelations not only deepen our appreciation of the forces shaping our planet, but also raise chilling questions about what may eventually come to pass. Before we start, smash the like and subscribe buttons for more updates. The Yellowstone caldera, formed during a cataclysmic eruption approximately 640,000 years ago, stretches across a wide swath of northwestern Wyoming. Long considered dormant but not extinct, this supervolcano has erupted violently multiple times in the past 2 million years. Each eruption dwarfed anything seen in modern recorded history. What scientists have now revealed is that the vast magma reservoir beneath the park is much larger, more complex, and more active than previously believed. Utilizing a suite of advanced imaging technologies, including magnetotelluric data, seismic tomography, and ground deformation modeling, researchers were able to construct a far more detailed picture of the magma system than ever before. The most startling discovery centers on the interconnectedness of two massive magma reservoirs, one shallow, just a few kilometers below the surface, and another significantly deeper, descending as far as 45 kilometers into the Earth's mantle. Previous models suggested that these chambers were largely isolated, but new data indicates a dynamic, fluid-filled connection between the two. This means that magma can move more freely between the chambers, potentially feeding the upper reservoir with a continuous supply of molten rock from below. It also suggests that the supervolcano may be more primed for activity than scientists had hoped. What intensifies the concern is the composition of the magma itself. The latest studies suggest that the upper reservoir holds a higher proportion of eruptible magma, molten rock capable of triggering an eruption, than earlier models indicated. While previous estimates pegged the volume of eruptible magma at around 10%, new measurements raised that figure significantly, in some areas exceeding 20%. This difference is more than just a numerical shift. It transforms our understanding of the system's readiness to erupt. An increase in eruptible material means that the pressure within the caldera could reach critical thresholds more easily, thereby lowering the barrier to a potential eruption. Seismic activity in and around Yellowstone has always drawn intense interest, but the newly interpreted data has identified specific swarms of micro-earthquakes that appear to align with pathways through which magma migrates. These seismic signals reveal that the magma is not static. It is moving, albeit slowly and unpredictably, through narrow corridors that wind their way upward. The implications are profound. This isn't a frozen giant waiting for a random trigger. It's a living, evolving system with internal dynamics that may be quietly steering it toward future instability. Adding to the complexity, scientists have identified a persistent pattern of ground uplift and subsidence within the caldera. Using satellite-based INSAR interferometric synthetic aperture radar and GPS instruments scattered throughout the park, researchers have detected cycles of inflation and deflation in the ground surface. These movements, sometimes measuring several centimeters per year, indicate that magma is accumulating, then partially draining or repositioning. Such behavior hints at a pressurized system under continuous flux, akin to a breathing subterranean beast. One particularly eerie detail concerns the heat flux measured at the surface of the park. Yellowstone is known for its geysers, hot springs, and fumaroles, features that are themselves symptomatic of geothermal intensity. However, scientists have recorded a notable increase in thermal output over recent years. While this could be linked to natural fluctuations, the spike in geothermal activity suggests an upward movement of magma or an intensifying interaction between subterranean fluids and rock. In short, the system appears to be becoming more restless. The terrifying potential of a Yellowstone super eruption lies not only in its explosivity, but in its far-reaching consequences. A full-scale eruption could eject thousands of cubic kilometers of ash, rock, and gas into the atmosphere. The immediate devastation would encompass several states, obliterating infrastructure and rendering large swaths of land uninhabitable. But the broader, more insidious threat is the atmospheric fallout. Ash clouds could circle the globe, blotting out sunlight and triggering a volcanic winter that would plunge temperatures, disrupt agriculture, and lead to cascading ecological and economic crises worldwide. What the new findings underscore is the need to recalibrate our risk assessments. Until now, many models operated under the assumption that Yellowstone was relatively quiescent, a geological relic slowly cooling and settling into dormancy. These recent discoveries suggest otherwise. The system is active, complex, and potentially closer to a tipping point than previously believed. Although there is no immediate indication of an impending eruption, the capacity for rapid change means that vigilance is imperative. Earth systems often behave non-linearly, with small perturbations leading to massive shifts. Yellowstone, it seems, may be no exception. Understanding the magma dynamics also reframes how scientists view other supervolcanoes across the planet. If Yellowstone's upper and lower reservoirs are more tightly coupled than once thought, similar structures might exist elsewhere, hidden beneath layers of rock and sediment. This insight could guide future monitoring and preparedness strategies, ensuring that humanity doesn't overlook the quiet giants resting beneath its feet. The lessons learned from Yellowstone may very well serve as the blueprint for global volcanic risk management. Another deeply unsettling aspect of the new data involves how quickly conditions can evolve within the magma system. Modeling based on fluid dynamics and rock permeability suggests that once a certain threshold is crossed, either through increased heat, pressure, or structural weakening, the transition from a stable system to an eruptive one could occur in a matter of weeks or even days. This narrow window for reaction underscores the importance of real-time monitoring and the deployment of early warning systems, especially in an area that attracts millions of tourists each year. Complicating matters further is the nature of Yellowstone's eruptions. Unlike stratovolcanoes that tend to erupt in narrow, localized events, supervolcanoes can erupt over broad regions through caldera-wide collapse. This means that an eruption wouldn't just blast through a single crater. It could rupture across a much wider area, emitting multiple vents and unleashing pyroclastic flows over hundreds of kilometers. The multi-directional nature of such an event would make containment or evacuation virtually impossible on short notice. The atmospheric implications of a Yellowstone eruption stretch far beyond the boundaries of the American West. A massive discharge of sulfur dioxide and volcanic ash could initiate a severe global cooling episode. Climate models estimate that average global temperatures could drop by several degrees Celsius, severely disrupting weather patterns and shortening growing seasons. Crop yields would suffer worldwide, particularly in already vulnerable regions. Food prices would skyrocket, supply chains would disintegrate, and mass migrations could ensue as entire populations seek refuge from increasingly uninhabitable conditions. The ecological aftermath would be no less dramatic. Ashfall could decimate forests, rivers could become acidic from volcanic runoff, and animal populations would be forced to migrate or perish. The cascading effects on biodiversity could take generations to reverse, if at all. While the Earth has endured supervolcano eruptions before, the impact on modern civilization, with its intricate web of interdependence, could be unprecedented. The dense urbanization and global trade that define today's world might amplify vulnerabilities that didn't exist in previous geologic eras. The human dimension of the Yellowstone revelation cannot be ignored. Communities surrounding the park live under the silent presence of this colossal geologic feature. For many, it is a source of pride and natural wonder. But for emergency planners, scientists, and policymakers, it is also a ticking clock whose rhythm is not fully understood. The challenge lies in preparing for a rare but catastrophic event without triggering undue panic. Yet these latest revelations demand a recalibration of public awareness. Emergency protocols, disaster simulations, and infrastructure reinforcement may need to be revisited with greater urgency. Another layer of concern lies in the potential for secondary hazards. Should Yellowstone erupt, it could destabilize nearby fault lines and trigger seismic activity across a wide radius. The shifting of magma chambers and the collapse of rock structures could generate massive earthquakes, landslides, and flooding from dammed rivers or melting snowpacks. These cascading disasters would exacerbate the primary eruption's toll, stretching emergency resources and magnifying the humanitarian crisis. Yellowstone's immense power is a reminder of Earth's capacity for change on a planetary scale. The magma chamber that churns beneath the park is a crucible of pressure and heat that predates human history and will likely outlast it. But for the first time, humanity possesses the tools to peer into this subterranean world with clarity. The revelations these tools provide are both a scientific triumph and a harrowing wake-up call. While these findings do not signal imminent doom, they dispel any illusion that Yellowstone is a static monument to ancient eruptions. It is in fact a dynamic system with the potential to unleash energy on a scale that defies human comprehension. The intricate dance of magma, rock, and gas beneath the surface continues, invisible but unrelenting, shaping the future in ways we can only begin to imagine. The scientific community now faces the monumental task of translating these discoveries into actionable knowledge. Improved monitoring networks, enhanced predictive models, and international cooperation will be essential to mitigate the risks posed by Yellowstone and other supervolcanoes. But even with the best technology and planning, the full scope of such a geologic event may always remain just beyond human control. The terrifying details emerging from Yellowstone's magma system serve not only as a stark reminder of nature's fury, but as an urgent call to preparedness. The ground may feel solid beneath our feet, but beneath that illusion lies a roiling sea of molten rock, ancient and unyielding, waiting for a moment, perhaps a tremor, a crack, a surge to reshape the world. Whether that moment comes in a decade or a millennium, one thing is now clear. Yellowstone is not done writing its story, and humanity is not merely a spectator. We are part of the narrative, whether we are ready or not. The Yellowstone revelations continue to unravel a deeper, more haunting narrative, one that extends beyond geology and reaches into the fabric of planetary processes, atmospheric systems, and even evolutionary consequences. With the discovery of a far more active and interconnected magma network, scientists are compelled to reassess not only the nature of supervolcanoes, but also how life on Earth responds to their intermittent awakenings. Every supervolcano eruption in Earth's history has marked a pivot in the planet's ecological and climatic stability. The disturbing complexity of Yellowstone's current magma architecture hints that we may be witnessing the early stages of such a pivot again. One of the lesser-known but significant implications of a more extensive and volatile magma system is its potential to distort the surrounding crust in subtle but consequential ways. Yellowstone's crust, already thinned and fractured by millennia of volcanic and tectonic stress, becomes more susceptible to doming and rifting as magma presses upward. Doming occurs when pressure from below arches the ground upward over large areas, stretching and cracking the overlying rock. This isn't merely a structural transformation, it's the precursor to surface failure. With cracks forming more easily and allowing gases and magma to seep through, the risk of hydrothermal explosions and new vent formations increases exponentially. These hydrothermal events are not on the same scale as a super eruption, but they are unpredictable and violently destructive in their own right. Steam-driven explosions occur when superheated water suddenly converts to steam, launching rock and debris skyward at velocities that rival traditional explosives. The revelation of enhanced fluid connectivity between magma chambers increases the likelihood of such events occurring more frequently or in previously dormant zones of the park. These events can obliterate wide swaths of forest, endanger human life, and indicate deeper systemic instability within the supervolcano. Another aspect that scientists have begun to focus on in light of these findings is the impact of deep crustal stress changes on surface geology and behavior. As magma continues to move upward, the redistribution of mass beneath the surface subtly shifts the balance of forces acting on the Earth's crust. This can alter regional fault systems, stress trajectories, and even trigger ground ruptures in seemingly unrelated zones. The enormous forces at play are not isolated beneath Yellowstone. They radiate outward, affecting distant geological systems. These relationships are non-linear and not fully understood, adding a layer of unpredictability that further elevates the potential threat. Furthermore, the increased mapping resolution has revealed what researchers are now calling magma fingers, thin, branching intrusions that snake upward from the deeper chamber. These narrow magma conduits may never reach the surface, but their ability to carry immense heat and volatiles could precondition the crust, weakening it over time. If several of these magma fingers converge or accumulate near the shallow chamber, they could set off a chain reaction of pressure buildup. Unlike a traditional eruption, which originates from a singular explosive vent, such a scenario could produce multiple eruption points over a broad area, a type of radial eruption that would make evacuation and response efforts nearly impossible. Perhaps the most unsettling discovery from the new data is the growing evidence of volatile saturation in the magma system. Volatiles, gases like carbon dioxide, sulfur dioxide, and water vapor, play a critical role in volcanic behavior. As magma ascends, the decreasing pressure allows these gases to exsolve, or separate from the melt. This exsolution process increases pressure within the magma chamber and is one of the key triggers for explosive eruptions. The concentration of volatiles in Yellowstone's upper reservoir is now believed to be significantly higher than previously estimated, suggesting that the magma is not only hotter and more mobile, but also dangerously gas-charged. This volatile-rich environment forms the perfect preconditions for explosive behavior on a continental scale. Another factor intensifying the seriousness of these revelations is Yellowstone's unique location within the North American tectonic plate. While most volcanic activity occurs near plate boundaries, Yellowstone is situated over a mantle plume, an upwelling of abnormally hot rock from deep within the Earth's mantle. This hotspot is stationary, but the North American plate drifts slowly over it, creating a chain of volcanic features stretching from Oregon to Wyoming. The implications here are twofold. First, the volcanic system is sustained by an enduring source of energy, and second, as the plate continues to move, stresses accumulate in the lithosphere above. This dynamic layering of geological forces makes the Yellowstone system uniquely unstable, particularly as the plate's motion continues to introduce new stresses to an already overstretched crust. Moreover, the interplay between surface water systems and the magma beneath introduces further complications. Yellowstone is home to an expansive hydrothermal network where groundwater seeps deep into the earth, heats up, and resurfaces in the form of geysers and hot springs. However, as the new data reveals increased magma mobility and heat flux, it suggests that water is reaching deeper levels than before. This deep penetration not only accelerates rock alteration and weakening, but also intensifies the volatile exchange between water and magma. When water meets magma at high pressures, it can flash to steam almost instantaneously, producing some of the most explosive and unpredictable volcanic events possible. The frequency and intensity of these interactions could rise in tandem with magma movement. Biologists and ecologists are also beginning to scrutinize the impact of subsurface changes on Yellowstone's complex ecosystem. As heat levels and gas emissions rise, soil chemistry is gradually shifting. Entire microbial communities that thrive in the geothermal features of Yellowstone are already showing signs of transformation. These microorganisms are not just curiosities, they're the foundation of the park's food web. Any disruption to their metabolic cycles could cascade upward, affecting everything from insects to apex predators like wolves and bears. The ecosystem has evolved in step with the geothermal landscape, and now that landscape is beginning to change in ways that could prove disruptive or even catastrophic. The park's rivers and lakes are also under threat. Increased thermal activity can raise water temperatures to levels unsafe for native fish species like cutthroat trout. Elevated sulfur dioxide emissions can acidify waters, endangering both aquatic and terrestrial life. These are not hypothetical concerns. Changes are already observable in water chemistry, as sensors installed throughout the park record variations that track closely with shifts in subterranean heat patterns. These subtle yet persistent changes paint a picture of an environment being slowly and steadily reshaped from below. Airborne impacts are another area of concern that stems directly from Yellowstone's potential for sudden activity. Even without a full-scale eruption, smaller explosive events or large-scale degassing episodes could release plumes of sulfur dioxide, carbon monoxide, and other noxious gases into the atmosphere. Such emissions can lead to localized health crises, especially for those with respiratory conditions. Depending on wind patterns, the reach of these gases could extend far beyond the park, affecting air quality across multiple states. With the increase in volatile concentrations beneath the surface, the possibility of large-scale degassing events is growing more plausible. Perhaps the most intellectually unsettling implication of these findings is what they mean for humanity's illusion of geological security. The vastness and relative stillness of Earth's surface give the impression of stability. But Yellowstone is a crack in that illusion, a place where the planet's deeper, more chaotic nature comes to the surface. These recent scientific insights are not just about the mechanics of magma and rock, but about our relationship with a world that is far more alive and volatile than most of us dare to imagine. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Yellowstone's magma system? What do you think will happen? We want to hear from you. Thank you for watching, and see you next time.